Okay, the first example I wanted to show you of how to use the Laplace transform to solve the circuit problem is a Thevinen problem. So Thevinen problem is an important techniques that you have to know about the circuit analysis. We've been using Thevinen in the traditional DC circuit. We also look at the phasor. Now we're going to use this in the Laplace transform. The techniques is the same. The way that you find the VTH, RTH is all the same, except that you transform that into an S domain for the Laplace transform. So let's look at how we solve this. The procedure of solving a Laplace transform problem is the following. So the first step is to find the initial value. The second step is after you find the initial value, you're going to convert your circuit into an S domain. Now, when you convert the circuit into the S domain, that including you have the source, so V sub t and I sub t, convert that into the V sub s and the I sub s. If you have them, if you have the equation, then you can convert them. If you have a graph, you know how to convert that as well. We did this a lot of different example already. Another thing you have to convert is that you have an inductor. If you have an inductor, that will become SL. If you have a capacitor, then this will be 1 over CS. If you have a resistor, simply just the same value. But then all this, the inductor capacitor, you might have an initial value, so you might need to add an initial value as well. And you look at the table 13.1. So I suggest that during the exam, you wanted to have this table available, so you can look at the table, try to change your circuit into an S-domain circuit. And after this, the next step is to use the Thevinen. The Thevinen techniques to solve the circuit. But this is going to be in the S domain. So everything is in Laplace. The last step is to convert that into a time domain. Okay, so this is a general step that you need to know how to use the Laplace transform. So nothing really new, except that you just need to know how to do a Laplace transform and also the inverse Laplace transform. Another thing that is new here is that because the Laplace transform method incorporate with the initial value, so you have to change your circuit. So that step 2 is also a crucial step that you have to know. So let's look at this problem and let me show you how we can use this step to find a solution. So the first step, let's find the initial value. Now we didn't give you the I sub s, so I should give you the I sub s for this plus. So let's say this I sub s, assume this is 10 U sub t amp. That's the source of here. Now, you know u sub t is the step function, meaning time is greater than 0. You have 10 amp, time less than 0, that's 0. So what is the initial value for the circuit? When time is less than 0, what is the value of the current across this inductor? Well, because there's no source at all when time is less than 0. So you know this is going to be it's going to be 0. And time 0 minus 0 plus, they are going to be the same because this is an inductor. Inductor cannot change its current instantly. So right at the beginning of the time, the inductor is going to have 0. So that means there's no energy stored in the inductor. Okay. All right, so that's the first step. And because this is a 0, so if this is a 0, then you simply just change all this components into the S domain without adding any of the initial value. So this is an easy one for this case. Then I simply just modify my circuit into an S domain. Now, for the this S domain is also like a phasor. You simply change all this component into the phasor. So let me just mark things in phasor on this graph. So 2H is the inductance of 2, then this will be SL, and that means this is a 2S. For the resistor, is simply the same value, just write down the constant. This one is going to be phi as well. Now your voltage in this case will become V naught of S, and our I of X will become an I X of S. So everything will become a phasor. Over here, this is a dependent source that will become a phasor as well. This will be your I sub S. Let's just write down what those things are if we know. So we know the source, the I sub S is equal to 10 U sub T, and you do a Laplace transform, this will become 10 over S. This is a very simple one. You can look at the table, you can find the solution. For the rest of them, we simply just change the inductor, and that's all. Okay, but then how do we solve the circuit? Well, we want to solve the circuit, and you have to use the Thevinen method. So let's look at how we solve the circuit in the Thevinen method. To find the Thevinen, you need to find the VTH, but this time we're going to use the S domain, and we also need to find the RTH. That's going to be an S domain. Well, sometimes people would just simply just write impedance had the same kind of meaning. So the Z, which is in the S domain, or RTH is in the S domain, this is 7 impedance. So let's find the VTH first. To find a VTH, you have to look at what is the part of the circuit you try to simulate. You try to make it into the Thevinen. The thing we interested is the V naught. We want to find a V naught, and that is our load. So on the left-hand side of the circuit, you can convert that into a Thevinen. So I'm going to open the node between this resistor. So this part is my load. In the left of the circuit, I want to convert it into a Thevinen. By doing that, then you look at the circuit. Well, this is the circuit that's redraw this, and we going to convert this one into an S domain as well. So this is our circuit. And you look at the circuit. Well, are there any current goes to the right? Well, it's open on the right hand side, so there's no current goes to the right hand side. So you can instantly know this current is going to be equal to 0 because there's no current goes to the right hand side. And then the rest of the thing that we need to solve is simply just the left hand side loop of the circuit. This one here is a voltage source. It's a current controlled voltage source. The voltage is equal to 2I sub x. Well, we just find out I sub x is equal to 0. That means this one is going to be 0. So you actually connect with a 0 voltage source of dependent source at here. If that is 0 voltage, what does that mean? If that is a 0 voltage, it simply means this is a wire. So you can look at this one just like a wire. Now at the bottom here, this is a phi omega. And we know in the S domain, it's just simply just phi. On the left-hand side, this one is our source, and we know the source is 10 over S. The voltage at this node is the voltage of the VTH. This is the open circuit voltage, which is our VTH. So this is our VTH, and we can find this VTH in the S domain. And this is a similar to your phasor analysis, similar to your any like a time domain circuit analysis. V equal to IR, and you can find the V, right? So this VTH is simply just your I in the S domain. This is actually the source times 5. That is your resistance. So that is equal to I sub S is 10 over S times 5. And I give you 50 over S. So that's our VTH, very simple. You can find this easily. The next thing is something that you have to know how to deal with a circuit and with a dependent source. How do you find the RTH or the ZTH in this case? There's two ways. So one is the testing source method, and the other way is what we call the short circuit method. Then you find the short circuit current. So I'm going to use the short circuit current method. When you use the short circuit current method, that you simply put a wire. So put a wire between the node. So there's an open node right now. I'm going to replace that with a wire, and the rest of the thing you don't change it. You don't even change the independent source. Just keep what that is. So let me redraw the circuit again, and let's look at what the circuit looks like. Now, don't assume the dependent source as a wire again, because this situation has been changed once we replace the right-hand side with a wire. When you put a wire, then you have a current go through, so it's no longer to be equal to 0 anymore. then you have to put that into consideration. So this will be the circuit. After we put a wire, this is the wire. And what we wanted to find out is that we want to find out what does the current go through here. This is the short circuit current, right? And if you look at the circuit and they told you this is I sub x, and actually I sub x is equal to this one here. So once you find out the I sub x, and that is your short circuit current. The inductor over here is 2S, and because there's no initial value, so you don't need to change anything. Otherwise, you have to use the table 13.1. The source over here still to be 10 over S. This is a 5, and over here, this is a 2 I sub x, and we use everything in terms of Laplace transform S domain. Now, how do we solve this? How do we get the current of I sub x in this problem? Now, you can use any kind of method that you learn from the chapter 4. I would probably just use a node analysis. Let me assume this is the node, and say this is a node of 1. I'm just going to assume the voltage of this node is V sub 1 of S. And by assuming that, I am looking at current go into this node. So I have a current coming from the left, which is equal to 10 over S. I also have current goes to the right, which is I sub x. And what about the current goes down? That's one of the current. I don't know, but I can write down what that current is. And just say this is I sub 1. Okay, so let's simplify this, make a note here. This is the V1 of S. The current coming from the left is 10 over S. Current goes to the right is IXS. The current goes down. Now, how do you find out the current goes down? Well, remember, we have another essential node here, goes to the ground. And you look at the voltage difference is going to be the current over your resistance. So if I can find the voltage difference between the top node and the bottom ground, then I can find out the current. So this one here is going to be something over 5. Now the top one here, you look at the current direction, the current start from the V1S. And it goes to the positive node. When you go to the positive node, you're going to plus the voltage. So you plus this voltage, and the voltage is 2Ix of S. And it goes to the ground will be minus 0. So that's nothing you have to subtract. And this is your current at this position. So now I have all this current. I can write down my equation, right? So my equation will be simply giving me the 10 over S, which is the current goes in, equal to the current goes out, where the current goes out is I sub x plus V1 over 5 plus 2 over 5, which will give me a 0.4 I sub x. But what is the V1 equal to? I have a V1 show up, but I need to find the I sub x. Well, if you look at the circuit, isn't the V1 as over 2S is your I, right? V equal to I and times impedance, where impedance to S. So I also know this one is equal to V1S over 2S. So I can put this one into this equation as well. So just replace this one here. That's equal to, so the V1 will be 2S Ix. Okay, so another way you can do is you can also replace the Ix into the Vs. That might be the thing we can do, but either way should give you the solution. So so if you do that, then you will find out what is Ix. Let's see. As a matter of fact, I did this before. I'm using the Vx. So let me write down the Vx equation over here to show you what the Vx looks like, how the equation looks like. If you representing everything in the V sub s, the V1s will be equal to 100 over 2s plus 3. Okay, so 2s plus 3. Then you find the I sub x, which I sub x of s, that is simply the V1s over 2s. So the Ix will be equal to 50s 2s plus 3. All right, so what is the purpose that we find I sub x? I sub x is my short circuit current. Once I find a short circuit current, I can find out what is the ZTH by using the VTH divided by the IX or ISC. That is your ZTH. So your ZTH is the VTH of S over your ZTH, your ITH. And that VTH is 50 over S divided by 50 over S 2S plus 3. And you can cancel out this 50 plus S, and it turns out this result of this one is 2S plus 3. So that is like your RTH, right? So that is your impedance in the S domain. All right, so what is this one would do for us? Once you convert this, then you can see your Thevinen circuit become this. Your Thevinen circuit is actually the circuit like this. This is your source. This is your VTH, which is a 50 over S. And you have an impedance over here. This impedance is 2S plus 3. And that will goes to your load. And you load on the right-hand side. The load is this one here. And this load is 5 omega. And you want to find out what is this one here. Right? So how do we find this voltage? Well, you look at the circuit, this is just simply a voltage divider. The voltage divider, the voltage across this phi, it depends on what is in front of this phi, right? So there's like a 2 resistor, but it's not a resistor, 2 impedance. Then you can find the voltage by using a voltage division. Then your V naught of S is simply equal to the source of the voltage times the summation of the resistance, which is 2S plus 3 plus 5. And on the top is going to be the resistor value, which is fine. And that will give you 125 over S plus 4. Now, the next thing over here, so we solved for the V naught S. We got a solution in the V naught S in the Laplace domain. The last thing that we need to do is to do the inverse Laplace transform. So the step 4, use the inverse Laplace transform. Okay, so you got very simple equation. Our V sub 0 is this equation over here. We can represent V naught S in terms of a simple term where you have a S with K1 plus S plus 4 with K2. And we just need to find what is the K1 and what is the K2. You can use the residual method, or you want to use the algebraic equation method to find the coefficient. Let me just use the residual. Use the residual method. The K1 is equal to the denominator multiplied with your voltage source, voltage S function. So there will be S V naught S. And now the S equal to 0, and you find the solution, and that will be the coefficient. So S multiplied with my V sub S will give me the 125 over S plus 4, and that S equal to 0, I got 125 or 105 divided by 4, that is 31.25. The K2, you use S plus 4 times V naught S, that the S equal to minus 4, and that would be 125 divided by S equal to minus 4, that gives you negative 31.25. And therefore, your V sub S, that's equal to 31.25, 1 over S minus 1 over S plus 4. Then you take the inverse Laplace transform of this, that would be very simple. So V naught of the T is equal to inverse Laplace transform of the V naught S, and that's 31.25. What is the first one? 1 over S, that's U sub T. What about the second one? Well, the second one is the S plus 4. If you look at the table, that will be the exponential multiplied with the U sub T. So that would be minus E minus 4T and U sub T. So if you take the U sub T out, that will be 31.25, 1 minus E minus 4T, U sub T, and this is the solution.